an is a positive real series, a sequence. Every member is positive. And also given that the limit of an plus 1 plus an plus 2 over an is positive infinity as n approaches infinity. And we were asked to show that this sequence is unbounded for any n is unbounded. Now, of course, we use proof by contradiction. Okay, what if it's bounded? What kind of contradiction can we have? So let's turn this condition into equivalent expression. That is, the reciprocal is tending towards 0. Right? Because that will be more useful. It's the same idea. Right? So an plus 1 plus an plus 2 tending towards 0. Right? So proof by contradiction. If an is bounded, right? In other words, an given, first of all, given to be positive, but it is bounded by some fixed positive real number, a strict positive. So what's going to happen? So if that's the case, then I can claim that an must tending towards 0. Why? Because if that's the case, right, this is less than or equal to m, that means its reciprocal must be bigger than or equal to m. Right? So in other words, an over an plus 1 plus an plus 2 bigger than or equal to, I replace this term with m because this is less than, so reciprocal is bigger than or equal to m, bigger than or equal to m, so bigger than 2m. Right, this is okay because m is strictly positive, cannot be 0. And also knowing that, first of all, this strictly positive, right? And also knowing that this is the given condition, right? Same idea. So tending towards 0. So we immediately say this use squeeze theorem, right? This squeezed by 0. So is this one. So this middle has to tend towards 0 as well. But 2m is a fixed positive, so which means I immediately have limit of an is obviously also 0. Right, this is obvious. And so how is this going to be helpful? Right? Contradiction will be, so given this condition, right? So which means given any epsilon bigger than 0, there exists a capital N as long as little n is bigger than or equal to capital N. Then we always have an over an plus 1 plus an plus 2 is always going to be less than epsilon. Right? That's the meaning of limit is 0. Absolute value. I don't need absolute value because everything is positive, right? Less than epsilon, according to definition. Starting from capital N, right? I multiply this part onto that side, so I can have a capital N less than epsilon times a capital N plus 1 plus a capital N plus 2. Right? So it says, as long as little n is bigger than or equal to this capital N, this inequality is always true. Therefore, I can apply the inequality to this and that as well. So that is immediately less than epsilon times this term can be loosened by replacing this by epsilon times the next two terms, right? That's the pattern. Next term after this, next term after this. So next term after this is what? Capital N plus 2. And next term after this is a capital N plus 3. Likewise, this can be loosened, replaced by epsilon times next term is a capital N plus 3 plus a capital N plus 4. Now, epsilon extracted out. Epsilon square. An plus 2, just itself. Yep, an plus 2. An plus 3, 2 times an plus 3. An plus 4. So briefly what I've done, first I interpret this condition into this equivalent statement. So proof by contradiction if we assume an is somehow bounded. Okay, bounded by some strictly positive number. Then we immediately concluded that limit of an has to be 0 in that case. Okay, according to the definition of the limit of this is 0. So for any epsilon bigger than 0, there exists a capital N as long as little n is bigger than or equal to this capital N. We always have this inequality. Then use a recursive relation. Apply it again and again, we reached this inequality. We can keep doing this. Right, following the same logic. This is less than epsilon square. This can be loosened by epsilon times an plus 3 plus an plus 4. This can be replaced by 2 epsilon times an plus 4 plus an plus 5. This can be loosened by epsilon times an plus 5 plus an plus 6. Again, we extract epsilon, right? The epsilon to the power of 3 times, so an plus 3, just 1, right? An plus 3. And an plus 4, 1 of them, 2 of it, 3 of that. 3 times an plus 4. An plus 5, how many? 2, 1, 3. 3 an plus 5. An plus 6, just 1. Okay, so what's the pattern here? Look, the coefficient of this is 1 to 1. It looks like a perfect square, right? Coefficient of this is 1, 3, 3, 1. Looks like binomial expansion, right? 1 is 3, choose 0. 3 is 3, choose 1. Right? 3 is 3, choose 2. 1 is 3, choose 3. Binomial expansion. Keep doing this. Less than epsilon to the power of 3. This again replaced by epsilon times an plus 4 times an plus 5 plus this can be loosened by 3 times epsilon times an plus 5 plus an plus 6 plus this can be replaced by 3 epsilon times an plus 6 plus an plus 7. This can be loosened by epsilon times an plus 7 plus an plus 8. Okay. So extract epsilon. Epsilon to the power of 4 times an plus 4, just 1. An plus 5, how many? 1, 3, 4 of that. 4 times an plus 5. An plus 6, 3 3 plus, that's 6. 6 an plus 6. An plus 7. 3, 1, so 4. 4 times an plus 7 plus an plus 8. Right, coefficient is what? 1, 4, 6, 4, 1. This is more obvious. Right, clearly 4 choose 0, 4 choose 1, 4 choose 2, because 4 choose 2 is what? 4 times 3, 12. 12 divided by 4, 6. Right, 4 choose 3, 4 choose 4. Right? So actually I replace every member, right, every an with, because I assume that it's bounded above by a m, right, by m, so less than equal. After replace every term with m, I extract m, so m times epsilon to the power 4. Right? Inside here, coefficient is 1. 1 is 4 choose 0. 4 is 4 choose 1. 6 is 4 choose 2. 4 is 4 choose 3. 1 is 4 choose 4. Right? So again, this clearly you can see that 1 times 1 to the power 4 times 1 to the power 0. 1 to the power 3 times 1 to the power 1. 1 to the power 2 times 1 to the power 2. So immediately, m times epsilon to the power 4 times 1 plus 1 to the power 4. Right? That is m times 2 to the power 4 times epsilon. So 2 times epsilon to the power 4. Right? So what can we do about that? Right? Well, what's nice about that is that we say epsilon is any positive works. So we say epsilon is 1 over 4, of course works, right? There is a capital N, of course, is dependent on epsilon, right? It has something to do with 1 over 4, but it's a fixed capital N, right? So m times 2 times epsilon is half to the power of 4. So I've loosened an, right? Less than this, less than that, less than this, less than this. And we can keep doing it, right? Here, there's no restriction, right? I can keep doing it forever. Here I loosen it once, twice, 3 times, 4 times, 5 times, 6 times, keep doing it. I loosen it 4 times, I have to the power of 4. I loosen it k times, I have m times half to the power of k. Right, clear. K is some positive integer, right? Can be arbitrarily large. In fact, let me write it down. We fixed epsilon, right? 1 over 4. Then we found a fixed capital N, we fix it, right? Then I copy this down. So a capital N is less than m times half to the power of k. Right? This is good because now I can fix capital N. I can let k approach infinity. It's totally perfectly legal, right? Because, right? So this is fixed, right? Strictly positive, right? Every term is given to be strictly positive. Of course, this is fixed term, strictly positive, but it's less than this. But this is actually approaching 0, right? Because k approach, right, half to the power of k, of course, approaches 0. M is fixed, right? K approaches positive, approaching infinity, right? So this is no problem. So how can the right-hand side approach 0 while still be bigger than this fixed positive, right? Something arbitrarily small, but bigger than a fixed positive number, right? It's impossible. So my proof by contradiction, right? Here's contradiction, so it means false, right? So an cannot be bounded; it must be unbounded.